particle acceleration and non-thermal processes in astrophysical jets. And the second part of this seminar will be given by Dr. Jiri Horak. He did his PhD at Charles University in Prague under supervision of Vladimir Karas. And he's a researcher in Astronomical Institute of the Czech Academy of Science, and his work is focused on the physics of accretion flows around neutron stars and black holes. So we appreciate your talks. And we will have some minutes for questions after each talk. And at the end of the seminar, we will also have some more minutes. Thank you.
Okay, thank you very much for the introduction, and it's a big pleasure for me to be back here and give this seminar. And today I will present some work that we have done last year in collaboration with some people that you may know, like Maria Victoria del Valle, and also with some collaborators abroad, Marco Padovani in Italy, Alexander Markowitz in France, and Francisco Suzuki Vidal in the UK. And I will talk about particle acceleration and magnetic field amplification in astrophysical jets, and I will focus in non-relativistic jets, in protostars, and also in nova outflows. And at the very end of my presentation, I will give you some insight of what we are planning to do in the future with laser plasmas. So in the next slide, there is an outline of the talk. So I will mostly focus on protostellar jets because what we have done, what we have published last year. Then I will talk a bit a new model for gamma ray emission in nova outflows, and finally I will say a few words about laboratory experiments and how we can get some information that can be useful for us in the lab. That we can use very controlled setup to understand better the physical processes in the universe, but by making an experiment. So I will start with young stellar objects. As you probably know, massive stars are created in these dense regions, and they are formed all together. And we think that the mass, there are a lot of evidence that the massive stars are formed at the top of these pillars, that we call the pillars of creation, or creation pillars. This is a HST image of Orion star forming region, and here we can see one jet here and another jet here. And this is infrared data, but from these shocks here we also have radio data. This is a zoom of this of one of these jets. You can see very nicely here the jet and also the bow shock. So in my work, or in what I will present today, I focus on the non-thermal processes here in the bow shocks. So this is another source. It is the source IRA 16547 that most of us know very well, and this source is very nice because we have a very clear and very detailed radio observation from the north and from the south lobes. So here is the central protostar is here. We have thermal jet here, the base of what the jet is created here, but when the jet terminates, like here and here, we see non-thermal emission. And we know that emission is non-thermal because the spectral index is negative. So both in the north and in the south, we have evidence of particle acceleration, in particular electrons, of relativistic electrons here and here. And this is what we made a model for this source. When in 2007, it was my first paper, and we studied these two sources, and we proposed that this source can be a gamma ray emitter. Nowadays, there are no detection of this source, But there are some claims of other sources that have been, well, there is a paper where they claim gamma ray emission detected by Fermi of another protostellar jet, not this one, but another one. We don't believe on this data very much because in gamma rays the spatial sensitivity or the resolution is not very good. So in the data that they have published, it is really huge size in the sky, and you can have from there several sources, not only the protostellar jet. So it is not easy to claim, or it is not straightforward to claim that the gamma ray emission is coming from a protostellar jet. But anyway, there are some claims of the detection of gamma rays from protostellar jet. But this I put it here as kind of example of how protostellar jet looks like in radio, because in the previous data, this infrared you see very beautiful jets, but when you observe the source in radio, it doesn't look so nicely. But anyway, for us this data is more important, because from here we can estimate, for instance, what is the flux, the energy in non-thermal particles with the diode. The next slide. So here we consider we consider 11 sources, 11 non-thermal lobes in protostellar jets, and what we plot here, it is the energy density in non-thermal electrons against the magnetic field. And you can see that in most of the cases, in order to explain the synchrotron data, or the synchrotron flux that it is here, we need magnetic fields that are quite large, I would say. So this is in milligauss, and you can see that mostly, for most of the sources, we need magnetic field between 0.1 and 10 milligauss. These magnetic fields are very large, so we don't expect to have these values of the magnetic field at the termination region of the jet, where it is it can be from 0.1 parsec up to 1 parsec from the central protostar. So the magnetic field there, the jet magnetic field, should be quite diluted. So if we have these magnetic fields at the termination region, it is because we expect to have some kind of local magnetic field amplification. Because if this synchrotron emission is produced only by compression of the jet magnetic field, then the value should be much lower. So because we need these magnetic fields to explain this synchrotron flux, we can argue that there is their magnetic field amplification. And the mechanism that we are using to, or we are considering to explain this magnetic field amplification, it is magnetic field amplification by non-resonant hybrid instabilities. What is this mechanism? You probably know that it has been proposed that in supernova remnants, the mechanism to explain the synchrotron emission in X-rays is by magnetic field amplification, and the mechanism to amplify the magnetic field, it is by protons with higher energy, by non-thermal protons. When you have this, when we introduce the current of non-thermal protons in the Maxwell in the plasma equations, you can have an extra force there, and this force makes it is a way to amplify the magnetic field by this mechanism that we call non-resonant instabilities or valence instabilities. Here I will not go deeply on it. I will just show you what we need to satisfy in order to have enough energy in the plasma to amplify the magnetic field by this mechanism. Basically, what we need, it is a significant energy in non-thermal protons, and this. So if this is the, okay, it will be in the next slide. So this is basically what is this our scenario. We have the jet termination shocks. When the jet terminates and impact with the ambient medium, we have a bow shock in the ambient medium and a rotor shock in the jet. And because in these sheds we consider the shed it is lighter than the ambient medium, the reverse shock it is more powerful than the Gauss shock, and we are considering particle acceleration in the reverse shock here. So electrons and protons are getting accelerated here by the Fermi-1 acceleration mechanism, and then electrons and protons can radiate here in the shock downstream region by different mechanisms. For instance, by synchrotron emission, they produce the emission that we see in radio. And in order to check if we can amplify the magnetic field by Bell instabilities, one parameter that we need to know it is the density in the plasma. And how we compute the density in the plasma, it is just by assuming a special geometry for the shed, and just we know the mass loss rate in the shed. That this is a parameter that you can estimate from the thermal emission in the shed at the base of the shed. So we know this value from the data. We assume that the shed velocity is 1,000 kilometers per second, and then this parameter that is the size of the shed. We take it from the radio data, and from this equation we can estimate the shed density, or we can have an estimation of the shed density. And then if we want to amplify the magnetic field by the Bell instability, what we need to certify it is this condition where this parameter it is proportional to the acceleration efficiency of protons, and this is the Mach number. So if we satisfy this condition, then we are sure that we can have this non-thermal mode here, and this is the way to amplify the magnetic field. So as we can see here, this parameter it is larger than 1 for our sources for a large values of the shed density and the shed magnetic field. We can see that this parameter it is easily satisfied in these sources because the shed it is dense, and because of that we have a lot of kinetic energy in the plasma to give to particles, to give to accelerate particles, and then these non-thermal protons will amplify the magnetic field. But having also a large density in protons in the plasma here, it can be also tricky because you can have also damping of instabilities. But this is something that we didn't consider in this paper. So if we satisfy this condition, the magnetic field can be amplified by these Bell instabilities, and this is the maximum growth rate of the instability that is mostly evaluated here. So we can see that we have the non-resonant mode even for low velocity shock at 300 kilometers per second. And we propose that the magnetic field in these sources it is amplified by the Bell instability. And so by comparing the magnetic field that we need to explain the synchrotron flux with the saturation magnetic field predicted by this Bell theory, we can constrain what is the magnetic field in the source. And we did it for these 11 sources in our sample. And after that, what we have done it is to compute the maximum energy in non-thermal particles, because if you amplify the magnetic field in this way, there is also a way you have also like an upper limit for the maximum energy of the particles. And we computed, for protons, and if you have a maximum energy of...
Sorry, what is the amplification factor, the final amplification factor?
Like a 100.
100.
Yes. And then, so we, by setting this constraint, that is the maximum growth rate multiplied by the size of this kind of characteristic time that you have in the plasma to amplify the magnetic field. So if you put this constraint in your source, you can estimate, or you can have an upper limit for the maximum energy of the protons. And because electrons in our model behave as test particles, so electrons cannot get maximum energy larger than this value. So this is also kind of maximum, like a maximum or upper limit for the maximum energy of electrons. But anyway, in our case, electrons get even lower energy because of synchrotron cooling. But for the protons, we estimate the maximum energy in this way, and in most of the cases, it is about between 0.1 and 1 TeV, the maximum energy of protons constrained in this way. And so we compute the gamma ray emission. So here you can see this from 1 GeV till from 0.1 GeV to 1 TeV, and we can see it in our sample, like in 3 of the sources in our sample, we can have detectable levels of gamma rays, and for these 3 sources, we made the spectral energy distribution from direct to gamma rays. This is what I have shown before. This is the gamma ray emission due to radiative bremsstrahlung, and this is the synchrotron data.
So one of these sources is the original one from 2007.
Yes. And now what we are doing is we are going deeply on the Fermi data with one colleague in Montpellier that she's very keen on analyzing this Fermi data, and she's taking this sample and going deeply on the data, trying to see if there is something there.
How different are these predictions from our original predictions in 2007?
Not too much. The main difference is on the maximum energy, but on the upper limits levels, not. What you can see there is that these sources are probably not good one for CTA, so probably CTA will not detect them. But Fermi, after 10 years of collecting data, it's a good instrument to take a look at for looking at these sources.
And the other source, 1648, which one?
Yeah, this I really don't know. We took a there is a paper studying non-thermal emission from massive protostars. In this, like there is a survey in the north and in the south, and we took data from there, and we select from there the best candidates. I mean the ones with better resolution, where we can see the non-thermal nodes better, also with because in this paper they said it is non-thermal when the spectral index is lower than minus 0.1. So we took like a more conservative way to do it, and we said lower than minus 0.3, because between 0.3 and minus 0.3 and minus 0.1, you can have a lot of contamination from thermal emission. So because we wanted to avoid that, we just made our constraint more conservative, and we took only sources with a spectral index lower than minus 0.3 in value. And with this, and also by taking only the ones with better spatial resolution, we select only 11 sources, but they have quite a lot.
About the radio observations, which are the sources? ARCA, and do you have anything from GMRT?
I think it's BLA.
So you don't have 600 megahertz?
No.
Do you have 350 megahertz?
I think all these sources are like at 8 gigahertz.
Sorry?
8 gigahertz.
8 gigahertz.
Because
With
we have
BLA.
600 megahertz, the GMRT source.
Yeah. Yeah.
It could
So
be interesting.
yes. We took this survey made by this group in I think the year in Dublin. Because we have a lot of sources with nice tables, so we took it from them. But we have everything I have done here, we have this model ready to apply the model to other sources if we have good the determination of the spectral index, and also we need what it is tricky for us. It is to constrain the size of the source. Well, you know that.
We have that for the same source.
Mm-hmm. Okay, yeah, we can discuss that, because it is if the resolution it is not good enough, it can be very tricky to determine the density in the plasma, because for the density we need to know what is the volume of the source, and this is why we are also being very conservative with the resolution, with the spatial resolution, because it goes with the size square. Then if you don't constrain the size of the source very well, then you have a lot of, you can really overestimate the density in the plasma. But yeah, if you have a good source, a good candidate, we can apply our model and we can see what it is. We can estimate the maximum energy and also the gamma ray flux. Yeah. So this is for protostellar jets, and one important thing it is that for the gamma ray emission, if it is hadronic gamma ray emission, what we need it is the high density in the thermal plasma in order to have like a large number of targets for proton collisions. And there is what we are studying now, both from the astrophysical point of view, but also from the laboratory experiment point of view, is a way to enhance this density in the plasma by having a special configuration of shocks. What we have done it is that if we have in the jet termination region and what we call the leading working surface, a combination of a radiative shock and an adiabatic shock, we found that this contact discontinuity, it is very, very unstable by related instabilities. So what it happens is that then this contact discontinuity here will be destroyed, and we have huge mixing here in this region. And why this is important? Because if this, imagine we have the jet coming from this direction. It is the density in the jet, and this is the density in the ambient medium. And in this protostellar jets, the ambient medium it is denser than the jet. So the density here it is much larger than the density here. So this when this shock is radiative and this is adiabatic, this configuration is very, very nice for gamma ray emission. Why? Because in this adiabatic shock we can accelerate the particles efficiently, because adiabatic shocks are better for particle acceleration than radiative shocks. So particles can be accelerated here, and then electrons can radiate here if you have magnetic field amplification, for instance, and produce radio emission. But for the case of protons, if we don't have here like a large densities for proton-proton collision, then the hadronic emission will not be efficient, and also lattice supreme will not be efficient either. So we need somehow to increase the density here, and by having this mixing here, it is a way to increase the density here, because if this shock is radiative, we know that the compression ratio it is much larger than 4. So in a radiative shock, we can compress the plasma even by a factor of 100. So if we have here in this, here in the contact discontinuity, a density that is 100 times larger than the density here, and then we can mix this dense layer here, and we can put some of these clamps with this density here, then particles that are accelerated here can diffuse up to these dense clamps and produce gamma ray emission by interaction with these very dense clamps from the ambient medium. So what we have done it is in this paper we found so similar solution by the first time of having the combination of adiabatic and adiabatic shock, because in all the previous papers people were considering even like 2 adiabatic shocks or 2 radiative shocks. And we did it for this special configuration, and we found that this contact discontinuity is very unstable by related instabilities. And you can find the details in this paper. And we apply this special configuration of shocks to protostellar jets. That it is more or less what I showed you before. in protostellar jets with 300 kilometers per second and 1,000 kilometers per second for the jet velocity, we can see that we have this combination of adiabatic and radiative shocks for a large value of parameters. This we already knew from before. So when we have these adiabatic and radiative shocks, so this is the adiabatic reverse shock, and this is radiative forward shock. This is how the temperature looks like, and density and temperature looks like. So we can see here that the density jump is much larger than 4, as it is here for adiabatic shocks.
And the diffusion of the protons occur under what regime? One regime, I guess not.
Well, it is not bomb. It is not bomb. I don't know. Oh, I didn't put it here, but Maria, she computed the power spectrum of the magnetic field, and we provide in the paper kind of estimation of the diffusion regime. It is not bomb. But it is sufficient enough to allow the particles to diffuse up to the clamps. And this is how the mixing looks like for the normal cooling, no cooling, and supercooling. And what it is interesting of this model is that for the case of nova outflows, you know that this nova emit gamma rays. So protostellar jet, we still don't know. I mean, there are no data, no detection of gamma rays from protostellar jet. But for the case of nova outflows, there are, I think, like 6, 7, or less than 10 sources that are gamma ray emitters by Fermi, but also by Hess. Hess detected last year one source in the TeV domain. And the standard way to explain the gamma ray emission is by saying that the shock is radiative, because these outflows are very dense. The density in these nova outflows can be like a 10 to 9 particles per cubic centimeter. So all of the models that you can see in the literature trying to explain the gamma ray emission from these sources assume that both the forward and the reverse shock are radiative. However, we found in this paper that there are a special combination of parameters that are non completely real. I mean, let's say, where we can have a combination of adiabatic and radiative shocks. And if you're in this condition, we know that we can amplify efficiently. We can accelerate the particles efficiently in the adiabatic shock, and then these particles can diffuse up to the clamps in the contact discontinuity, and there they can produce the gamma ray emission. And we have proposed this model because in the model that you find nowadays in the literature, the way that they model the gamma ray, the particle acceleration is very handy, because they assume that the shock, it is radiative, but the radiative shocks are so if you want to do it properly, you see the efficiency is very, very low. So it is what we propose in this paper. It is an alternative way to produce the gamma ray emission in nova outflow by considering this special configuration of shock, like it is for like a adiabatic reverse shock, and radiative forward shock.
But your main assumption is that the velocity of the ship is higher, three times.
But it is in the case of RS of Fucus, I think it's the name. It is 3,000 kilometers per second. I'm sorry.
Yes.
Yeah.
Quick question. So how you determine what are the different regions?
We use this. So the idea it is that for the shock to be adiabatic or radiative, we compare the cooling length with the size of the source. So if cooling is more efficient than adiabatic escape, then the shock is radiative. But then if particles manage to escape before radiation, before radiating significant part of the energy, then the shock is adiabatic. So we just set this parameter, this constraint.
Okay.
Mm-hmm. So this is the source that has been detected last year by Hess, So when we published the paper, we didn't have the data yet. We only have the claim in ATAL, and then 3 months later, Hess published the spectral energy distribution. So we didn't compute or we didn't make any prediction for the set, but we just compute the cooling length by considering different diffusion and escape and cooling processes. And what we want to do now is to use the data that has been published by Hess and to trying to explain this data in our model, in this special configuration of shocks.
Is there any radio emission associated with this?
I think yes.
Yes, and it's a group that is following the nova decline with VLA observations.
Is it non-thermal or is it thermal?
I don't know.
What it is important in this source, it is that it is also detected by Hess, because all other nova detected in gamma rays has been detected by Fermi, but this one also by Hess. So it means a even higher energy of the particles. But last year when we submitted the paper, we didn't have any indication of this detection. But then when the report came, say, okay, but now we know that there is this source. Can you please say something about this? And so Maria, more or less, she took what we knew from the ATEL, and so we say, so this is what we can say now, and we can apply our model to this source, because the velocity is quite large. It's 3,000 kilometers per second. And so now we want to model better the source, because we have the Hess data that they published the spectral energy distribution, but this is what we have up to now. But what we say in this paper, it is that even in nova outflows we can have adiabatic shocks, because it has people were only time considering that these shocks, because they are very dense, the shocks are always radiative, but we show that it's not the case. We can have a special configuration of parameters where the shock is adiabatic, and this is better for the particle acceleration, because if we see gamma rays and even TeV photons by Hess, you need quite efficient acceleration of protons and electrons. And so finally, I will tell you something about laboratory experiments. You know that nowadays, or since the last 5 or 10 years, not more than 10 years, laboratory experiments are becoming more and more popular in high energy astrophysics. And the reason of that, it is because now with high power lasers, we can create shocks in the laboratory. And why it is important? Because we can control them, because it is an experiment, we control what is going there. That it is something that astronomers we are not used to it, to control something. So, but if we make an experiment, we can control what it is, what we want to see, and we can design the experiment for a special study, right? So if we want to study this particular thing, we can design, or of course with a lot of limitations, but we are able to perform experiments that can tell us something about astrophysical conditions. And here, as an example, I put this experiment that has been published, and the result has been published maybe 2 years ago in Nature. And it is because it was the first time that they managed to create a collisionless shock in the lab. You know, because all the shocks in the universe, in astrophysical sources are collisionless, but in experiments they are collisional. The reason of that, it is because if the laser, what you have, it is you have a laser coming here, and the laser goes to a special target. And when you have the collision of the laser with the target, you create a plasma here. Yeah? And this, if you do it twice, you have plasma coming here and plasma coming here, and you create a shock in the middle. this is what they do all the time in these experiments. But because it lasts for very very short period of time, this shock doesn't have time to be collisionless. You only see the creation of the shock, and because the shock is created by collision of particles, so you only see when the shock is still in this collisional period. If we want to see a collisionless shock, we need to allow this situation to last for longer time. And for doing that, you need a laser with higher power. And this is what we are able to do now. We have lasers with power enough to have this situation for a longer time in nanoseconds, and allow the shock to be in the collisionless phase, let's say.
So what is the condition that you need to satisfy in order to get the collisionless shock in the experiment?
Well, you need to last it for longer time because.
But why?
Because if not, the shock is still in the particles are like going this way, and the particles don't have time to collide and to create the shock. Yeah. So you need first to allow the particles to collide and to create the shock. And once the shock is created, then you will see that these particles you will see that the particles can flow away and having this mean-free path larger than the width of the shock. At the beginning of the when these plasmas are in the first in the first interaction phase, they are still even in the collision phase. The shock, because the shock it is not even formed. Then the shocks form, particles are still colliding to each other, and then after that, particles can go away, and you have this kind of or you have this shock, and you have particles with energy larger enough that the particles can flow through the shock, and the shock it is for that particles the shock it is collisionless. And this is why we need lasers with higher power that we didn't have it before, and now, or we didn't have it before for kind of science experiment, because these lasers were used since long time ago for like military things, and for that they have a lot of power, but for science purpose, only nowadays we have enough power to use it in the lab and to create this what we call collisionless shock. And the first one that has been done or that has been published was in this paper by this group in the National Emission Facility in the US. And this is their setup. It is quite a standard setup. You have a laser going to a target, and then you have this plasma coming this way, and you send this way, and you create a shock here. Another difficult thing on doing this experiment is that you need to somehow take the information from that, because you perform the experiment. But then you need to measure, for instance, the temperature of the plasma, the velocity, the magnetic field, all these things that can be important for us. And this is what we call the diagnosis. So how we diagnose the experiment, how we take the information from it. And there are not too many diagnoses. So in different, like for instance here in NIT, they have quite good ones, but they're still not enough for astrophysical purpose. And this is so one important thing. It is like in this experiment, they were not able to estimate the magnetic field. They create here their own magnetic field by varying stabilities, but they were not able to measure what is the value of the magnetic field.
But you can put an external magnetic field and check whether particles are accelerated, trying to detect, for instance, synchrotron radiation.
Yeah, yes. This, in principle, yes, but they don't have a way to measure all these things. If you put usually they don't put external magnetic field. They have only the magnetic field in the laser that is very low. And what they do it is that they have when they design the experiment, they also make a peak simulation with the same parameters as in the experiment. And then they run the simulation, and they expect that what we see in the experiment is the same as what is in the simulation, because there are the same parameters. They run peak simulation with the same parameters as in the experiment. But the tricky point with the peak simulation is that in the peak simulation, in order to make the simulation fast enough, we need to use artificial ratio between the mass of the electrons and the mass of the protons. It is not the real 10 to minus 3, but it is 10 to minus 2, 10 to minus 1, because if you don't do it this way, then the simulation takes really, really long time. And we cannot do it in even in this case that we have a lot of computational power, they had to use this artificial mass ratio between electrons and protons. This is why the comparison between the peak simulation and the situation in the lab, it is not straightforward, let's say, because in the experiment you have the real mass ratio because it is real experiment, but in the simulation you don't have the real mass ratio between the particles. But
I imagine that in principle you might want to determine whether you are accelerating or not electrons in your experiment independently of the simulations, right? So in that case, I can put a stronger magnetic field from outside and try to detect synchrotron emission. If I detect synchrotron emission, this means that I have accelerated electrons in there, and then I can determine the spectrum, right?
Yeah, but then, so there are two things. The first one is that this is very short time. So how the shock lasts there for nanoseconds. So we need to be able to accelerate the particles in this time scale, because then the shock disappears. Because this laser, it is not a continuous laser. They shoot is like a shot. So they shoot this target with the laser, and then this lasts as much as it lasts, and yeah, it lasts as much as the power you put in the here. But then you need this acceleration mechanism to be efficient enough to accelerate the electrons in this nanosecond time, let's say. And this is one thing. When they see particle acceleration, they see only that the particle cross the shock 2 or 3 times, but not more. And then they say, okay, we extrapolate because then the shock disappears. So we don't know what happens after.
And how do they know that the particle crossed the shock for just 3 times?
Well,
how do you determine that?
They do with the simulation, with the peak simulation.
With the simulation?
Yeah. Because for this diagnosis, it is, as I told you, it is very limited what they can do. They can take a photo and they see in X-ray what is the temperature of the plasma, for instance. What else they can do? The magnetic field they can estimate it in a special way, but in this case they didn't do it. But there is a way to estimate the magnetic field. Synchrotron emission, it is, and how you will estimate it. You need to put a synchrotron detector here, somewhere in the. This is it is.
No, yes, I understand.
So it is. This is the difficult part of this experiment, that it is hard to diagnose. And what they do, it is this peak simulation. They run a simulation as with the parameters here, but with the limitation of the peak simulation, that they use this reduced mass ratio. But it is the way. So usually you perform the simulation before running the experiments, and when you apply for the time, you apply for need. It is kind of a telescope. You apply for some data there. So you have to provide them the simulation. You say, okay, I run the simulation, and this is what we expect to see. And if it is interesting enough, you will get some nanosecond.
What is the size of the chamber where the shock is formed?
Well, for instance, the chamber in Prague, it is quite, the one to have in Prague, it is kind of, I don't know, okay, this size, 4 meters. Yeah, it's quite big for the standard. But for instance, in Prague we have a laser that it will be we can use it, I think maybe next year we can start using it, And what is the important thing of this laser infrared? It is that it is high repetition. We can perform the experiment many times in one day, because in MIF you can do only one shot. So when you have time there, you have one shot, and what you get, you get. You don't have like kind of a statistic. So in Prague, we will be able to do a statistic and run the same experiment several times.
But what kind of parameters can you change in the experiment?
So you can change, for instance, this distance between the targets. Yeah. You can also change what is the material of the target, because how the target is, what is the composition of the material there. It is also the composition of your plasma here.
The power of the laser.
The most important thing is the power of the laser. But this is something that you cannot. So you have it is like a telescope, right? You have what you have, and then you can change something in your setup. The power, it is the power that it is given by the lab, let's say, by the laser that they have.
Do you have a notion of the energy scale that you handle in the lasers? How much energy?
So this laser, like the laser, when we say like high power laser, we talk about petawatts. This is like the most powerful laser we have nowadays for scientific purpose.
Okay.
And but what I wanted to say here it is that it is now it's becoming more and more popular in high energy astrophysics to perform this kind of experiments, because there are a lot of if we make a good design of the experiment, you see that it is quite. It looks quite simple, right? You just have two plasma, they collide, and you create a shock. So that's it. But then what it is tricky is how you get the information that you want to do, or how, if you want to see, for instance, there are other experiments where they want to see turbulence in the magnetic field. So what they do, they just have one laser here, one target, and here they make this plasma. They don't have any shock. They just put here like a grid, right?
Like a what?
Grid, like a grid.
Yeah.
And then they make the plasma to pass through this grid. And then after, the plasma is turbulent. And then they see there, they can estimate, for instance, the power spectrum of the magnetic field and all these things that are also very useful for us, right? But in that case, there are no shocks, only just the plasma passing through grid with a special size that you can design also the size of the grid. And you can study turbulence in the magnetic field or turbulence in the plasma. You can also inject from outside, some particles, some protons with a particular energy, and this is what the group from Oxford they are doing now for studying magnetic field amplification by the Bell instabilities. They will have a shock, and then they plan to inject some protons there and to see if these protons can destabilize the non-resonant modes.
What is the medium inside the chamber? It's just vacuum, or do you have some medium? Some medium. What is the medium
it's
inside?
vacuum.
It's vacuum.
Mm-hmm. Yeah.
How do you know if you reach like the plasma state of the matter? Is there a way to say, okay, this is really a plasma?
Well, I think it depends on the power here and the composition of your target. And these targets, these targets are kind of how to say commercial. So there are a lot of companies that make these targets for you. In Prague, we do it ourselves. If it is simple thing, if we want something more complicated, you have to buy to some companies. But we are also able to do our own targets in the lab in Prague. But here, what I wanted to show it is that this experiment got a lot of how to say. It was very, very popular because they managed to create the collisionless shock by the first time in the lab, and they also claim that they see particles. So they see here magnetic field amplification by Bell instabilities, and they claim that they accelerate the particles and a lot of things. You can take a look at the paper, and you can see that there are a lot of things that they cannot really compare easily with reality, or with not with reality, with astrophysical source. Because of course, what you have in the experiment, it is reality, it is there. But then to compare this with the supernova random, for instance, it is not straightforward. So what we do, it is, in order, if we want to make this experiment with some meaning, that with something that can tell us something about astrophysics, we need to have this like the Mach number, Reynolds numbers, similar to the Mach number and Reynolds number, for instance, in the supernova randoms. And then we are sure that the situation it is the same. But having this, what we call true similarity, or exactly the same, like having Mach number 10 here and Mach number 10 in the supernova random, it is very, very tricky. It is not easy. So usually you have a Mach number, in both cases, larger than 1. But if it is like a big difference between both cases, the similarity is not, it is okay, but it is not good. What is happening here, maybe it has nothing to do with what is going on in supernova randoms. And one thing, or what I usually criticize for this experiment, is that in supernova randoms are very, very popular among all these experimentalists. But we know that there are a lot of astrophysical sources, but they have also shocks, and they're making this similarity study is much easier if you take another source, not the supernova random. For instance, protostellar jets are much better for making these scaling studies, because the velocity of the protostellar jet, it is very similar to the velocity, because here you can get 1,000 kilometers per second, maximum 2,000. I think this is the maximum you can get here. So, and these are the typical velocity we have in protostellar jet. But if you go to supernova random, here the velocities are like 10,000, 30,000 kilometers per second. And because velocity, it is one of the few parameters that you cannot scale. All the others you can scale with this similarity law, but not the velocity of the plasma. So having similar velocity is quite important for having a good.
The velocity of the plasma inside the chamber,
yeah.
you measured it?
So here, this is, you can estimate it if you know the composition of your target and the power of your laser. You can estimate what is the velocity at different, because then this expands, right? But you can get, you can compute, you can do the equations, and you can see what is the velocity at different locations. And you can get as maximum, I think, 2,000 kilometers per second for this high power laser. So these velocities are good for protostellar jet, but are quite low for scaling supernova randoms. So this is one special case that I wanted to mention you, because it is nowadays very popular experiment. There are other experiments with much lower, with different facilities, but where they study protostellar jets and shocks in protostellar jets. And in this paper by Francisco Suzuki Vidal, the same. They have a plasma here, this plasma collide, and because this plasma, the velocity is larger than the velocity here, you have this bow shock in this that looks like this. And they managed to, in this paper, to study some mixing, the formation of the shock. It is collisional. It is not collisionless, but it's collisional. But they see some instabilities and some mixing in this shock. And in the paper that we have done with Francisco and Maria Victoria, we made the scaling for protostellar jets and also for nova. And so you can see that some parameters are. So for instance, the Reynolds number are, in the case of the of the astrophysical source is 10 to 10, and in the lab is 10 to 4. So in both cases it's larger than 1, but there's a big difference. So we have to, even when Francisco is saying that it's a good scaling, if you look at the numbers, it is not real scaling. Real scaling means that these numbers, this point, these numbers, and this number, particular number, are the same in both. But it is very, very difficult to have it. So this is everything I wanted to tell you today. So concerning protostella shape, we model 11 sources by considering that the determination shock is a combination of adiabatic and radiative shock. And we found that in 2 of them, we have detectable levels of gamma rays by Fermi. And if we consider a little of mixing, then we can increase the level, the gamma ray emission level that we have predicted, and even other sources can also be detectable with Fermi. And for the case of nova outflows, we propose an alternative scenario to explain the gamma ray emission by considering adiabatic shocks instead of radiative shocks, as it is considered nowadays in the models that you can find in the literature. We discussed in our paper this particular source that has been detected last year by Hess in the TeV domain, and also for both for novas and from protostellar shapes, we can perform some experiments in the lab in order to study what we have doing in these papers, this mixing by the plasma, and also diffusion. Like what we want to do, it is to make the particles to diffuse from the adiabatic shock to the mixing layer, and to see if these particles there can produce gamma rays in a better way than without this mixing. And that's it. Thank you very much.
So, I think there were already several questions during the talk, and we are kind of late, so maybe we can go straight with the talk, and maybe we can add something to say from the today. So that
Thank you. So after this very advanced talk, I will have to talk about something rather simple, and it is kind of very kind of, one would say, elementary problem. No, suppose that you have a star which is radiating, and around the star there is accretion base. So the question is, what will happen, or how this accretion disk will be modified by the radiation which is emerging from the star, and what will happen. So, thank you. And so I start with something very old, and just to remind you, very well-known fact, right, that there exists some limit of radiation of luminosity of the spherical star, when you will find out actually that by interaction with the radiation field, you are getting some force on the particle, and then if the luminosity is greater than some limit, then the particle is not longer kind of bound to the surface of the star by gravity, but it can kind of escape from the gravitational field. It's based on the fact that both the radiative flux and gravitational force are decaying with the square root or with the square of the distance, which is a well-known fact in Newtonian theory. Of course, in general relativity it's a little bit different, and then you can find that for kind of limited range of some luminosities there exists some kind of equilibrium positions where the particle can kind of stay, and this is kind of well known, or I don't know how much well known, but it's one of the results of actually the paper of Marek Abramovich, George Ellis and Antonio Lanza in 80s. But this range of luminosity is kind of very limited. So of course, from this point of view, we see that there exists some kind of limit on the luminosity, and then the interesting observation is that actually a lot of neutron stars accrete and even radiate quite close to the Eddington limit. So obviously this limit when radiation dynamically affects the matter around can be quite important. So in addition, it's not only like interesting problem, but maybe it can be even useful in some applications. Thank you. And this is the moral which our professors were all the time telling us: never start to solve the problem before you know the answer. So what we kind of suppose, or what are the main effects which we kind of await, or what we are kind of having in mind. So first of all, if you have some star and some particle going around, orbiting, for example, then we know that, of course, the radiation is carrying some energy, so this energy can kind of come to the particle or to the fluid, so the radiation itself is kind of affecting the thermal balance of this fluid, right, around. So this is different energy balance. Then the second effect would be like dynamical effect. So first of all, if most of the radiation is more or less kind of radial, then it's carrying some radial momentum, and then you kind of expect that this momentum of the radiation, when it goes to the particle, it exerts some force. So you expect that this force will slightly reduce or will act against the gravity. So what you expect that if the particle will be moving around, it will probably be moving with different speed. No, it will probably reduce the angular velocity. So what you expect, if you would imagine like accretion disk around, you would expect a little bit different rotation profile, right? It will not be like Keplerian rotation, but maybe Keplerian rotation with reduced mass, right? If both of them are scaled with the square of the distance. And then there is the third effect, which everyone who ever run in the rain knows very well. If you are running in the rain, you know that you are wet mostly from the front side, right? And that is well known fact. It's called aberration effect, and the reason is that your velocity is somehow added to the velocity of the drops, so you experience most of the rain from front side. And this poor particle is having the same experience actually. Even all the radiation kind of is going more or less if it is not moving, so from front and from back it would be the same. When it is moving, it's again this aberration effect that causes that most of the collisions with the photons experienced by this particle is from the front side. So basically this particle would probably lose angular momentum, and this angular momentum will be kind of will be channeled out by the radiation which is kind of emerging from the particle, or to the scattered radiation basically.
So the particle moves in this direction.
if the particle moves in this direction, then it will be kind of
force
slowed down.
yeah.
Yeah, exactly. So this is the free effect, and this is what we expect. What is kind of surprising that this effect is actually important. This effect is very important, but somehow this effect is not important. Which at the beginning I would say that it is actually the one which would dominate, but at the end it's not like that. And this is the talk will be about that. Okay, and now we are moving to some calculations, but I hope that it will not be too technical, right? So here it's just kind of some basically assumptions. So I wanted to kind of be as much relativistic as possible. So kind of to keep all the relativistic effects which we are having, to have this radiation drag and so on. So, but at the same time to be not very complicated. So I use the most simple space-time, which is kind of static axisymmetric space-time, and at the end I will talk about Schwarzschild space-time, right? So it's kind of spherical symmetry at the end. Fluid will be described by kind of well-known stress energy tensor, which looks for ideal fluid like this, and then there is like the some components of the shear viscosity tensor, which is like traditional in accretion disk theory, and in the comoving frame it will have just R phi component, like what we are used to in accretion disk. And then the dynamics, of course, follows from the relativistic conservation laws. So this is the conservation of the rest mass, basically. So this rho is rest mass density, and then you have like the conservation of energy and momentum, which in relativity is written in this way. And because we want to kind of calculate also this effect of radiation, so the effects of radiation will be included by this phi on the right hand side, which is radiative force. Right? It basically tells you how much of energy and momentum goes to the fluid per unit of time from the radiative field, right? And then, of course, and to have life as simple as possible, so for the radiative transfer, I assume that I have gray material, which means that nothing depends on frequency of the radiation. Isotropic radiative processes, the most simple, and yeah, this is just technical note that it's when it is like that it makes sense to kind of evaluate this radiative force in the fluid comoving frame, which is and of course, like traditional in accretion disk theory, vertical integration in order to reduce two-dimensional problem to one-dimensional. And this is quite limitation, no advection. So it will be basically something like Novikov-Thorne or Shakura-Tsunaev around radiating object. Right? Thank you. And this is how these equations look like. So on the left is kind of something what is well known, right? So this is somehow mass conservation. You can integrate radially. You have like one integration constant, which is this m dot accretion rate, and somehow it's usually expressed in this kind of little bit complicated way, right? This gamma is something like Lorentz factor of the radial motion with respect to the co-rotation frame. Sigma is vertically integrated density. Capital B is against the radial velocity of the fluid with respect to the frame which is co-rotating with the fluid, right? So the people who are doing the slim disk and ADAS somehow likes this quantities describe the flow. So I'm using the same. So this is mass conservation, angular momentum conservation. The phi equation of this previous conservation law looks like this. And here on the right hand side, you already see that there is this azimuthal radiative force I will be talking about. Like if there is 0, then you can even integrate this equation, and then you will get like people are doing in like Shakura-Tsunaev did, for example. In relativity, already here for Novikov-Thorne, you have some non-zero term here, which is describing actually the the flow of the angular momentum taken by photons from the accretion flow, right? So, but here there would be also like this effects of incoming radiation. This is like a radial momentum, so basically radial Euler equations looks like this. Again, this is standard, this is something new on the right hand side. Vertical momentum equations look like this. Without this, it would be just hydrostatic equilibrium, but there is also some force on the right hand side. And energy conservation, in the case when there is no advection, looks very simply like Shakura-Tsunaev assumption that what is generated at a given radius is immediately radiated. So, thank you. So this was kind of technical, and this is a little bit more interesting actually, and that is if you would think about what kind of radiation field is around, right? So at one point you can say there are two components, right? First of all, there is like radiation which is coming from the star, penetrating the disk and then somehow interacting. And second, there is another source of radiation, which is accretion disk itself, right? Because it's kind of heated by viscosity and radiating black body radiation away. And somehow you have this mixture of these two, and they are quite different, right? So, for example, for this thermal radiation, or even reprocessed or kind of absorbed and radiated again, its geometry is very simple because it's more or less isotropic, right? Because all these processes are isotropic, so you expect that it will be like nearly isotropic, which is fine. But for this incident radiation, which is coming from star, it is highly anisotropic, right? It's just coming from this direction where the star is. And so some people are using, like for the calculating radiative transfer, they are using Eddington approximation, right? But Eddington approximation is good when you have really nearly isotropic radiation field. When you have like very anisotropic, then it's kind of only approximation and sometimes even not very good. For example, if we would assume that radiation from this star is kind of more or less isotropic here, so it's coming from all directions the same, then we would probably kind of lose this effect of like momentum transfer and this kind of Eddington effect which we would like to kind of use.
So this radiation coming from the star is the thermal radiation from the surface of the star?
Yes. Yeah.
For instance, if you have accretion, you will have an excess of radiation in the polar cap, right?
Yeah.
Do you take
No. This star is kind of isotropically radiating.
Okay.
Yeah. And of course, it's not here, it's somewhere here, right? But it's just kind of, yeah. This is one complication, but one can like include. But I want to be like as simple as possible at the first like moment, right? So the idea is that actually one can split this kind of radiation field into these two components. And so the splitting is a little bit artificial. When the photon is radiated from the star, going to disk, it's all the time in the first component. Once it's absorbed or scattered, the scattered radiation is counted into the second component, right? So the first component is very anisotropic, but it's only absorbed. And the second component is nearly isotropic. And of course, there is also source term from the first component. This is the radiation which is scattered and immediately counted in the second component. The idea is that actually for the first component, I can just use formal solution. I can easily kind of integrate this equation, right, which is like constant coefficient, first order ordinary differential equation. The second component is complicated, but because it's nearly isotropic, I can use Eddington approximation. So this is like the way how one can deal with that. It's not my invention, I just steal it from the people who are using planetary atmospheres. But it's quite rare as example that sometimes with very small tricks you can do a lot, right? Like here, for example, which is not very often. Okay. So this is just like sketch how to do it. So first component is only absorbed, so the solution looks something like that, blah blah blah. Then second component looks like that, okay, and then you can integrate it and even find the analytic solution because you are using this Eddington approximation. And once you have all these like radiative field evaluated, you can calculate what is the radiation force, which is what we are mostly interested. So this is the general formula, right? Here is what how much momentum is absorbed, and here is how much momentum is actually radiated, and you integrate over all directions. And if you use this kind of yes, thank you. If you use all these kind of radiation field quantities derived previously, you can even evaluate what is this radiative force. And there is one interesting thing, and that is that since the this second component, which is kind of radiated or scattered component, is nearly isotropic, it doesn't enter here too much. So most of the radiative force in the radial and azimuthal direction are mostly done by this first component, which looks like this. And then if you look at that, this tau h is basically optical thickness of the disk, like vertically, half like from the surface to the equator. That is why there is this 2. And if you say, okay, this optical thickness is very high, this is negative, then this is like exponential of very high negative number. So this you can kind of, for very optically thick disk, you can kind of neglect, and then you will get something like integral of the radiative density times like 2 vectors, which you can see is nothing else but the stress energy tensor component of the radiation, right? On the other hand, if tau is very small, then you can expand this exponential, and then if you expand, it's 1 minus something. This 1 cancel this 1, and this minus something is tau over nz, which cancel this nz. So then at the end you will get like the intensity times only the radial component. So at the end you will get something like this, which is quite, I was quite surprised by this, simply because it means that for optically thick material and optically thin material, you can calculate the radiative force always from the stress energy tensor of the radiation. But for these two cases, it's completely different component. And why it is like that, I am trying to interpret here. And so again, if you would like calculate the radiative force for optically thin flow, since it is if it is optically thin, it behaves like all the particles are experiencing more or less the same radiative field, right? Because if it is optically thin, then all of them are getting the same radiative field. And then if you want to evaluate the force, you will just take force to one particle, which is like cross-section times the flux, radiative force, and then how many particles you have like in one column, which you can calculate like this. And if you just multiply these two, you will get exactly this. On the other hand, for optically thick flow, it's completely different because first of all, radiation field is different in different heights in the disk. And basically, if you have some radiation which is coming to the disk, then the disk will take all the momentum which the radiation has, right? So if you would like to calculate how much momentum is lost from the radiation to the disk, it's easy. You just calculate how much momentum goes to the disk per unit of time, per unit of surface, which is exactly this component of the stress energy tensor. So at the end you will get this. And whatever the optical thickness is, it doesn't matter because this is what is available in the radiation field, right? So there are these two extremes and these two different components of the stress energy tensor. And we are approaching, yes, this is just kind of one nice idea from this old paper of Abramovich, Ellis and Lanza, and that is that actually you can find analytic expression for this radiation stress energy tensor in the case of the star, which is quite easy because if you look at this picture, for example, if you are here, you observe the star, you see the star as a like big circle on your sky, and the stress energy tensor depends only on how on angular size of this star on your local sky, and this angle, which is this kind of here denoted by A, you can analytically calculate, and this is what these people were doing. So there is like simple analytic expression for this that is just some ratio of these two quantities. One evaluate at the stellar surface and the other one evaluate at some distance. So the message from this is that you have analytic expression for this T alpha beta in the local in the reference frame of the local observer. That means that you can evaluate it also in whatever other frame, like Boyer-Linglis coordinates and so on. And so that was about radiation. Then there is another note, and that is that actually in the case of radiative pressure dominated disk, you don't have like determined the vertical structure, right? Because if you write down the equation for the vertical momentum or vertical hydrostatic equilibrium, then you have equilibrium between this tidal vertical gravity, right, which is this, and then it is compensated exactly by the radiative flux. So you don't have any expression for the density if you calculate so this is the vertical momentum equation. if you calculate derivative, you will find out something like this, that the radiated is constant in the vertical direction, and from this you can calculate like thickness of the disk. And and this is already known to Sakura Tsunaev in one of their papers. And but what you don't know is actually how the density profile look like, and for this you have to assume something. So people usually are assuming the most simple velocity density profile, which is constant density actually vertically, and this is what I am using here as well. And here is like one application. So so far I was talking about all these equations, right? And now how these equations look like for the case of standard Sakura-Tsunaev-like or Novikov-Thorne disk, right? So in Novikov-Thorne we don't have advection, right? So we know that like from the radial force equation, what usually if Novikov-Thorne survive is just kind of centrifugal force and gravitational force, right? Or not in relativity, but in Sakura-Tsunaev. So here, this equation is kind of modified by another term, which is coming exactly from this radiation force, right? This is this one. So this is like radial momentum balance. In the azimuthal momentum balance, again, this is how Novikov-Thorne looks like, and here modification again like azimuthal radiation force. So this is kind of radial radiation force, and this is effect of azimuthal radiation force. Now there are some dimensionless quantities, and most important are these three parameters. One is alpha, like classical alpha in accretion disk theory. Then the other one is kind of dimensionless accretion rate in terms of Eddington accretion rate, and something what sometimes it's kind of called the gamma factor, which is kind of how much the star is super or sub-Eddingtonian, right? So if gamma is equal 1, it means that the star is radiating at exactly like Eddington luminosity. So there are these three kind of dimensionless parameters, and if you look at that, and that was the surprise actually of me, you will find out that actually this radial force is given by multiplication of all the three. Right? We assume that all the three will be probably less than 1. No? The star shouldn't radiate more than Eddington, and also it's reasonable to assume that the accretion rate is not more than Eddington. Alpha is, I don't know, 0.01 from numerical simulations, or from observation 0.1. So this should be less than 1 definitely, and quite strongly, because it's multiplication of all these three. So it's reasonable to say this is still 0. On the other hand, if you look at the azimuthal momentum balance, there is this ratio of these two accretion rates. Of these two powers, right? Accretion power and the radiative power. So this can be actually as much as 1, right? And then, so what I will talk about is exactly this regime, where I will say that this is small and this has some value. Okay. Why it is like that, and why it is like that the radial momentum from the radiation has playing so negligible role in the dynamics of the disk. And I think the one explanation is actually in this paper done by Yun Fukue in 2015, which is devoted to very simple problem, and that is again like Eddington luminosity, So Eddington did it like 100 years ago, but he is now considering not proton and electron or a single like particle, but he is now assuming really some cloud with some optical thickness. And the question is, so is Eddington luminosity, does it apply for this setup? And he found out that actually no. But what he's called critical luminosity is exactly luminosity when this cloud would be kind of levitating, right? And actually he found out that this critical luminosity very much depends on the optical depth of this cloud. This is quite surprising because I always thought that Eddington luminosity is actually really saying that if you have cloud and some star which is kind of super Eddington neon, then this cloud would really kind of go away. But this is not like that. Actually, it very much depends on the optical thickness of the cloud. If it is very optically thick, then super Eddington doesn't mean anything. And the reason how I understand that is actually that if you have like some brick or cloud, there is radiation field coming here, so there is only limited amount of the momentum that can be transferred to this object from the radiation field, right? And the point is that if it is optically thick, then all this momentum is actually taken by this lower level layer of the object. So this is all these particles get some momentum from the radiation. On the other hand, to the gravity, all the object is contributing, right? So even for the point is that this object will get from the radiation field like the same amount, like for example this object, right? But the gravitational force is double in this case. So that is why this optical depth actually plays the role. And I think since we are talking about optically thick accretion disk, it's exactly the same effect, right? So that's simply this amount of radiation which is accretion disk getting from the radiation is not enough simply to play some important role. Okay, and then we are going to the very end, and that is, so what I did is neglect, like in the radial equation, this term of the radiation, and solve only azimuthal equation, which looks like this, and again up to here it looks like standard Novikov-Thorne, and here is this additional azimuthal radiation force. And what is nice that you can even integrate it analytically, and at the end you will get something like that, where this effect of radiation is described by this k equals 0 is like standard Novikov-Thorne, and so this is the integration, and then there is of course some integration constant, which is the main trouble here. And what I did is so far is the same as Novikov-Thorne did, and that is that I assume that at the marginally stable orbit you have like 0 torque of viscous forces, and then the result look like this. So what you see here is kind of radial coordinate, and here is the heating rate, right? And then as k grows, the luminosity of the star grows. So k equals 0 is standard Novikov-Thorne profile, which we know. But of course, as you increase the radiation of the star, then you are kind of more efficiently removing angular momentum from the disk by this radiation. So you don't need such much viscous heating, or you don't need so much the viscosity, and that is why the viscous heating is reduced. On the same time, it goes to 0 at some kind of finite radius, which I think is signalizing that this boundary condition is not alright. Right? So probably one has to invent something more clever, and that is that really you have to solve this transonic flow and find this critical point where is the sonic radius and do it really properly. But it's not algebraic problem, but then it's more complicated. And this is just to summarize, so still in work in progress, but I still think that the effects of radiation field is kind of already a little bit visible, and probably if one do it really correctly, numerically, founding this location of the sonic points and so on, one would find out that actually the inner edge of the disk is probably dependent on the luminosity of the star, which I think is already visible at these solutions, but of course one should really set the correct boundary condition, not like this simple. So this is the first point. Second, of course, it would be interesting to see how advection change the picture. So irradiated slim disk would be nice to have, and also it would be nice to see like how the radiation or irradiation change the thermal stability of the disk. So for example, like this S-shaped curves, right? You know that there is like ADAF, slim disk, and standard disk. So how these curves are changed by the irradiation, and what would be also quite interesting is to see how the flow looks like in the plunging region. So if you would have like star which is well inside its marginally stable orbit, then you have like accretion, then like somewhere it entered the plunging region, so it starts to plunge, and then the matter should still decelerate before kind of falling down on the star. So how this boundary layer would look like, or perhaps there could be also some shocks near the surface of the star. But it's still something what one should explore. And this was the main reason why I actually was entering this, and that is how the perturbations of such disk would look like. The question is, for example, how whether there will be the same discoseismic modes, and how this frequency of this main oscillation modes of the disk will change with the luminosity, with some hope that it will may be relevant, for example, for quasi-periodic oscillations around neutron stars. And then there are more complicated things like effects of magnetic fields and so on, but it's complicated. Okay, so thank you very much.